I'll get going. Welcome everyone to our session on synthetic source injection. Thank you for joining us, remote people. Please let us know if something goes horribly wrong. We can't promise we'll be able to fix it, but we will try. So this is going to be hopefully an overview of sort of what we have in the stack at the moment, a little intro to some modifications we're making, as well as a couple of demos on how to use what we have at the moment so people can start to use this to address some of their science questions. So before we start, please be nice to each other. Do not hug people who do not want to be hugged. This applies all the time, not just when COVID is here, but particularly when COVID is around. Make sure you give people their space and be civil. And if you need to report code of conduct things, yell, or go and see one of the many ombudspersons that have been introduced throughout this meeting. Yes, we will be monitoring the Slack channel, but not the Blue Jeans chat, because we can barely work Blue Jeans in one window without having to press buttons. So please don't ask questions in the Blue Jeans chat unless you wish to be ignored. So, an introduction to synthetic source injection. Why do we want to do this? That's going to be the first thing we discuss. And then we're going to go through what we could do before, what is new in the current refactoring we've been doing, and then some demos about how to do that. And then what we're going to start to make regularly available to people with data access without you having to do any extra work, because that's my favorite type of work. What sort of checks have we looked into so far? And then we'd like to finish this off with a discussion from people and feedback on what would be useful. We cannot promise that we will be able to introduce every feature every person would like, but the whole point of this code is for it to be useful for science users to be able to enhance and prepare their science. And if it is not, then there is no point to it. So we would like to know what will help you do your science and prepare for real Rubin data. So why do we want some synthetic source injection? DP0 doesn't include some object types. We've heard this come up recently over this thing. People have talked about my favorite celestial object is not in DP0. What do I do? My favorite celestial objects are not in DP0 because high redshift quasars are incredibly rare. And if I would like more than one per 1,000 square degrees, I need to make them myself. Other people's favorite celestial objects are also not there. So we hope to talk you through how you can make sure that you get 10,000 per square degree. Also, we use this for QA. It's a really useful tool because we know what truth is. So this is another good reason why we would want to do this. So, Lee, do you want to take over here?
Yep, sure, absolutely can do. I hope you can see me and hear me okay. I can't see you. Oh, well, that's fine. As long as you can hear me, that's the important thing. I can't see you either. I'm just imagining the room is packed full with thousands of people cramming in. That's my impression. So hello, my name is Lee Kelvin. I'm another member of the DM team here at Princeton, working alongside Sophie. Sophie, Josh, and I have been hard at work refactoring the code, as Sophie mentioned earlier. So up until now, the code that we've been using are basically summarized in these two screenshots here. We've been using the insert fakes task, process CCD with fakes. So this code allowed us to inject bulge disk, complex statistic models, point sources, and images if you've pre-prepared your own FITS images, for example. And this code served us well. We've been using it for quite some time now, doing a lot of QA and a lot of science and supporting external groups using this software. So it's been quite useful. However, there are some areas that we wanted to improve on for some time. We've been discussing improvements to be made to this code base for quite some time. So next slide, please.
It doesn't want to give me the next slide. Why has it stopped?
There we go. Okay, thank you. Okay, so yeah, as I say, there are some limitations with the current code framework. So the framework right now is very monolithic. So it's what that means is it's quite hard to change how and when you inject sources into your pipeline. So something that's been an active topic of discussion is we might want to inject sources earlier in the data reduction process to allow certain tasks, such as background subtraction, for example, to operate more effectively on images with synthetic sources included. There's another issue, which is that the ingestion of input catalogs is a little bit tricky right now. We're hoping to build tools that help users do a better job of doing that. Also, the formats for sources were very strictly defined. So point source is fine and good, but the bulge disk model is bulge plus disk, and there wasn't previously a way to trivially to do something different if you wanted to construct a different type of synthetic model. And the last bullet point is this word fakes. So you'll notice that we've been trying to move away from using the word fakes and talk about synthetic sources or source injection for various reasons. However, as with many things in Rubin, CalX PVI is one example that springs to mind. We do still drop this into our language every now and then, so you may hear that word crop up. Next slide, please. Okay, so we've been very busy developing a whole new repo. So on GitHub there, you can see the link. It's called Source Injection. And all of our code, all of our source injection code will now live here going forward. So on the right-hand side of the screen, you can see that the 4 key files where all this code lives. All the classes and the free functions that provide the kind of heft of doing the job of injecting sources. These are functional classes that allow you that wrap around GalSim and create GalSim objects, and then inject into the image and do all the photometric calibration, WCS bookkeeping, and things for you without an issue. All of this right now lives on a ticket branch. You can see that there listed as the second link, DM34253. We will very shortly be merging this to the main branch. We've been holding off for a number of reasons, one of which being we wanted to get feedback from this session to talk to the people in the room about extra things that we might consider adding in. Next slide, please. Yes, so all the new code will live in that repo, as I mentioned. It's now completely modular, so this should tick off that first box, which is we wanted to facilitate being able to inject sources anywhere in the data reduction process and make that very easy for your own science. If you want to do something we haven't considered you wanted to do, you might want it to do, should now be more feasible in the new framework. The second bullet point here is that one of the big changes we've made is we've done away with anything bulge disk. So now that we inject single CIRSIC components for the extended sources, we inject single CIRSIC components. We're still injecting point sources, and we're still very soon we'll be able to inject images again, fits images if that's your interest. But we decided to simplify down to single CIRSIC components because this then allows you to construct whatever complex model you want. So by having multiple rows in an input catalog, all of which can be CIRSICs of different descriptions, you can stack them up and build a very complex bulge, disk, bar, pseudo bulge, whatever you want kind of model. And that's now completely feasible and very trivial to do. And it also keeps the code base looking very clean and nice, simplified. We have a number of new pipeline YAMLs. So in Gen 3 world, everything lives in pipelines. We have a HyperSpriteCam pipeline, and we have EC2 LSST-CAM InSim pipeline right now. These are very trivial to set up. There's no reason why we can't add, for example, a DCAM pipeline to inject synthetic sources of DCAM imaging. So that's something we can certainly look into if there's interest in that. And then the last point there is, again, that the code has been significantly refactored to make it simpler and easier to maintain, and hopefully logical to those who want to dive in and understand exactly what's going on. Okay, next slide, please. Oh, yep, so these are the new, so within the pipelines are a couple of new subsets. There's the inject visit subset, and there's the inject coad subset. As the name suggests, they inject into visits and coads. You can see the inputs required for these two subsets. So the visit, you take a CalX, a PVI, a processed visit image, and you inject your synthetic source into that to produce an SI CalX. And in the coad case, you start with a deep coad and you end up with an SI underscore deep coad. So SI underscore is the kind of prefix that lives alongside everything in this repo. Okay, next slide, please. Okay, so over to me for a demo. So I'd like to take you through, Sophie and I are going to take you through a couple of different ways to actually inject synthetic sources into imaging that we have on disk. So in my demo right now, I'm going to inject a series of extended SERSIC sources into a single DC2 visit. I'm going to share this. I'm going to steal the screen in a moment, but before I do, there's a link there to GitHub where I've also uploaded a fully rendered version of this notebook for you to follow along if you'd rather do things that way. You can find these slides on our session page if you need to click the link, or don't worry about typing the whole thing in. I think Sophie's also put a link to the slides pinned in the Slack channel, so you can go there as well if you wish. Okay, so I'm going to try stealing the screen. Give me a second. Okay. Hopefully you can see my VS Code window. Is that showing up for everybody?
We can see your screen, Lee. There's been a request to zoom in a little bit more.
Let me see what I can do.
And also actually shrink your face, because your face is already tiny. It's just the room thing. Unless you can make your face giant.
Not sure. How is that for size? Is that good for people in the room?
Yeah, just press the little arrow top right as well, or top left, whatever.
Sorry, what?
Is that on our screen? Okay, I need to press the arrow.
Go ahead, Lee. We're ready.
I'm good to go? Okay, fantastic. Sorry. That's a bit hard to hear sometimes. Okay, fantastic. So this is a very simple source injection demo. So a very quick summary. We're going to use the Butler to find a collection, and then with a collection, we're going to find a calyx in DC2. And then once we have that, we're going to set up a very simple input catalog, which will discuss how, what columns you need to set up this catalog, for example. We're going to ingest that into the data repository, and then we're finally going to run the source injection task itself and generate a few plots just to have a look at what we're doing. So I ran this notebook this morning. I'm not going to make the folly of actually trying to run a notebook live. But you just have to believe me that I ran this 20 minutes ago and things worked. So there we go. Yes, we have a series of imports. There's nothing outlandish there. We're using Afw Display to display all the plots we'll be making later on. Okay, so the first thing we do is instantiate a Butler. So this is on our development machine up at NCSA, which will very shortly be switched off. So some of these links will change, no doubt. But here's where our DC2 repo lives on that machine. We instantiate a Butler in this simple way here. The first thing I'm going to do is find a collection. So I'm going to use the Butler registry query collections method just to query for any glob that matches this string, and it finds these whole list of 5 collections here. I'm going to select the first one, this 2.2i runs DP0.1 collection as my input. So I'm going to look for PVI calibrated exposures in that collection. Okay. So now we have a collection. We're going to query data sets. So I want to find a calyx. So I'm going to look in one of the regularly processed tracts, tract 3828, and query data sets for a calyx in that input collection. My data query is very simply this. It's the LSSTCAM IMSIM DC2 instrument using the DC2 sky map within that tract. And I'm only looking for detector 1 just to find a single detector. So that gives me 156 matches, 156 hits, and I've just selected one of those, which looks quite nice for the purpose of this demo, which gives me this dataset ref. So dataset refs look like this. It's a dataset type that has the dataset type calyx here. It gives you the dimensions associated with that type, and then the data ID, and where it lives on disk, and the pointer to the memory coordinates, and the run that lives in. I've just extracted the data ID here using .dataID method to get that information. Okay, so we have all the information we need now to finally grab an image. So we use butler.get, give it our data ID, the input collection, and our dataset type, and that gives us an exposure. These exposures are quite nice. They have three main parts: an image, a mask, and a variance plane. And we'll be looking at two of those today further on down. Okay, so we're going to use Afw Display to have a quick look at this. So I'm not going to go into the details of matplotlib and plotting, but needless to say, this is what these data look like. So on the left, you can see the CalExp, which I've scaled. It's Arcshine scaling, and I've somewhat smoothed the image as well with a Gaussian kernel, just to bring out some of that LSB structure and not focus so much on the noise. So you can see there's a lovely big galaxy here in the middle of this detector. On the right-hand side here, you can see the associated mask, the mask plane. I've just squashed all the bits down into a very small dynamic range, so you don't get that distinction as to whether these bits are indicating a detection or an edge or any other features. But it's quite a nice way to visualize all those hotspots. All right, so we have the input CalExp that we want to inject a synthetic source into. Next, we're going to generate a very simple input catalog. So I'm going to inject 100 Sursic sources into this image. So I just randomly assign them in X and Y coordinates on the image. And then I generate the remaining columns. So you can see that the logic above here, but I'll show the head of the catalog here. So a Sursic component has 7 free parameters, some kind of RA-dec or XY coordinate, a magnitude, semi-major axis, it's the half-light radius along the semi-major axis, an axis ratio, so that's B over A, the same minor axis divided by the same major, the position angle, and the Sursic index. So all of those are listed there. I'm generating Sursic indices anywhere from 0.5, so a Gaussian, all the way up to 4, so a de Vaucouleurs type system. So those are the 7 free parameters you need to define a Sursic. Sophie later on will do the opposite of this and be injecting point sources, which require only an RA-dec and a mag, so you don't need any of those extra columns. However, you always do need this final column, source type, which tells the repo what kind of Gaussian object it wants to inject. So is it a galaxy, then that's a Sursic function. If it's star, then that's a point source, and so on. Okay, so we have a very simple input catalog. Next thing we need to do is register this collection where this catalog will live. So we can't just feed in this catalog as is. We need to first ingest it into the Butler. So the process for doing this requires that we register the collection, and then we ingest this pandas data frame into that collection, so it can then be used as an input for source injection. So there's a few steps here. I won't go into too many details about them. We set up a writable Butler, which use with care, I would say, because you can make changes on disk when you're using a writable Butler. We're going to inject into this collection here, ULS Kelvin SI demo, and then there's some try except logic just to remove the collection if it exists. And then finally, we're going to register the collection here as a run type collection. Okay, so we now have a collection. We can also register our dataset type if this hasn't been done before. The repo needs to know about the dimensions and the storage class of all new dataset types that it sees. If this has been done before, then don't worry about it. You'll run this command and you'll end up with, as I have done here, just a false, which tells you, okay, you didn't need to do that. That dataset type already exists. No harm done. If that's a new dataset type, then this will return true, and you'll have registered it. So it knows what to expect when we finally upload an SI cat, that it needs these dimensions. Okay, and then finally we ingest the input catalog into the repo. So we're all ready to go. We use the writable butler.put to put the input catalog with this dataset type, with this data ID, with this into this input collection. and we're good to go. The data ID is just simply defined here in the tracked and sky map that we set up earlier. Okay, there's kind of, I think, one last couple of last steps before we actually get to the fun stuff of injecting the sources. So now we're kind of we have all the input data ready to go. We're now down to getting the Python in line. So we instantiate our visit inject config. This is a visit we're injecting into. So we get our config set up, which looks like this here. So I've displayed all the different config options for this particular class right now. All of these can be edited to change, if you have different column naming definitions, for example, or if you want to use a different type of photometric catalog, or all the things you can see here. All of those options are configurable. And then finally, we instantiate the visit inject task using that config class there. That's all ready to go. Okay, so the visit inject task itself requires that the input catalog is in the form of a deferred dataset handle. So this is a little bit, maybe a little bit unfamiliar to some people in the room. So deferred dataset handle is an object which performs an immediate registry lookup. It doesn't immediately grab the data at that time. That can be performed later on. So this is quite easy to get as well using the Butler get deferred. Again, you give your dataset type, your data ID, and the collection you're interested in. And it looks like this. If you have a look at that deferred dataset handle, it's very similar to the dataset ref in many ways. And that's kind of the end of all the setting up. So we're ready to run now the source injection task. So as an input, there are 5 inputs required. You need the catalog, the input exposure, the WCS and photometric calibration information, and then finally the sky map. We haven't got the sky map yet, but that's very trivial to get using Butler.get. I'll show you that in a moment. As an output, this task produces 2 things. So it produces an output exposure with synthetic sources injected, and it produces an output source injection catalog, which is just a very simple QA catalog that has essentially the same as your input catalog, but it has XY pixel coordinates appended as well. So you know exactly what XY coordinates it was. Okay, so that's how you run it. So it's very simple. There's just getting the sky map on this first line here, and then the actual run method is very simply this, which gives you those 2 outputs, which we extract here on lines 10 and 11. And that gives us this catalog, which again, as I mentioned, is exactly the same as the input catalog, but it now has columns X and Y here. So you can see the actual pixel coordinates of those injected sources. So let's take a look. Again, we're going to use Afw Display. So on the left here, you're seeing the before. This is the Calyx image you've already seen. And on the right, you're seeing the source injected Calyx image. So you can see there's a number of extended sources now that have joined this region, populated this particular detector, which is quite nice. We can zoom in a little bit to that nice big bright galaxy that was already there. And you can see this galaxy now has a few notable friends living alongside in the Bermuda Triangle of galaxies. It's quite nice. We can also pull a difference image, which is quite nice to look at as well. So if we take if we take the source injected Calyx and then subtract off the original Calyx, you should only be left with the difference, which are the injected synthetic sources. We can do that, and when we do that, we end up with an image that looks like this. So you can see again on the left here, that's the difference image. It's the exact same scaling as all the other images, and all the coordinates. And on the right-hand side, I've plotted the same image again, but I've overlaid circles just as a kind of proof that everything is where we wanted it to be. So this is the end of the notebook. So this is kind of step-by-step going through how you would do source injection, all within Python. You can do it all in the notebook. I hope you've been following along. At the bottom of each of these cells is recorded the time it took to run these cells. So they're all typically 1 second, 2 seconds. I think the largest time sync was the actual injection itself, which
Yeah, does anyone have any questions for Lee before we move on? Keith, come. People, when you have questions, come and stand at the front of the microphone.
Thanks, Lee. This was really informative. A quick question. How in the notebook did you ensure that the processing of the image and source detection was identical to the original processing?
So can you fill me in a little bit what you mean by processing exactly? Are you referring to source detection and background estimation, all that kind of stuff?
That's right. And so as you're getting to the ends of the cells in the notebook, there was a source catalog that was produced, and the question is, how did you ensure that the configuration of the source detection to produce that catalog was the same as the pre-source injection analysis?
Right, I understand now. Thank you for that. Yeah, that's a great question, and thanks for asking because it gives me a chance to clarify something. So the catalog that I showed there is not a source catalog in the same way. That there's been no extra detection steps run here. There's been no extra background subtraction. The whole purpose of this demo is very simply just to inject synthetic sources into an image. Once you have that image, that SI CalExp, you can then go back and rerun all of the standard DRP tasks that you may want to run, characterize image, calibrate, and so on. And all you have to do is change your connection type for your input, from whatever it is, from CalExp to an SI CalExp. So in this notebook, and I did write about this, but thank you for reminding me to mention it because I forgot to say it out loud. There's no actual redetection done in this. For the purposes of this notebook, there's no redetection done. I believe Sophie's demo 2, goes a little bit further than mine and actually, tries to get into some of the specifics about generating those kind of catalogs. So I'll perhaps defer to Sophie on that for more information.
Hi, Lee. This is Ian Sullivan. I have 2 questions. The first is, when you're injecting these sources, how are you handling the variance plane?
Right. So, right now, so the behavior right now is exactly as it was in the prior code. So I don't think there's any special modifications made to the variance plane. Certainly in my simple demo, that's not the case. However, that should be picked up in subsequent processing, which, again, as I mentioned in the last question.
Sorry, Lee. So we're not currently doing anything to the variance plane with the source injection. It is a topic we have for discussion later about if we want to and what we want to do. I know that when this was first written, people who are better at things than I am, like Jim Bosch, had opinions on this, and I just followed their guidance. I will defer to Jim Bosch on almost everything. So, yeah, but it's up for discussion later.
Sounds good. So the other question is, when you're injecting these sources into the CalExp, is the source injection affected any way by properties of the CalExp, such as the PSF size or anything like that?
Yeah, well, absolutely. I mean, there is an aperture correction that takes place. We've actually been discussing that this morning for other reasons. So that kind of information does filter through. Absolutely, yeah.
And the model is convolved with the PSF, like before injection.
Yeah.
Thanks, Lee. This is Eli. I do have an opinion on the variance plane. Our measurement test will not work unless the Poisson counts from the sources are in the variance plane, or it will get the errors wrong. I recently was dealing with this, but my question is, so that was really cool to see it all in Python, but some of these things would be nice as a pipe task. Is that available? That's what Sophie's
Yeah.
about to ship. Okay.
Well, if there are no further questions, Eli has provided the perfect segue into demo 2. So-
Sadly, there is one more question.
all right. But yes is the short answer, Eli.
Breaking the flow, but yeah. So this is Douglas Tucker. I mean, just a basic question. I'm not being a source injection beginner. So for galaxy bulbs, do those need to be injected separately? It looked like you just had you just had a single parameter for the galaxies. It looked like it was just disks.
Yeah. So actually, that's a great question. So the way we had things before, we were calling them bulge plus disk, but you could assign any Cersic index you wanted to those two components. So your bulge could have a Cersic index of 0.5, and your disk could have a Cersic index of 0.5, and the names didn't quite make sense. The framework now is that everything is a single Cersic of any given Cersic index. And that allows you to construct whatever complex source you want. So if you wanted a bulge disk system, you could set up an input catalog where row 1 is coordinates xy, Cersic index of n equals 4, and then row 2 is the same coordinates xy and Cersic index of 1 for the disk or whatever. And you can keep adding to that as long as you want. So all of those components can be stacked on top of each other at the exact same centroid, if you will. And you have the full flexibility to be able to go away and make whatever bulge, disk, bar, whatever kind of component you want to add in.
Thank you very much.
Okay, if we don't have any more, I don't think there's anything on Slack specifically for Lee, right? Then I will move on and I will try and answer Eli's question, but with an otherwise much more boring demo. So the first thing you need to do, and Lee covered this, but I put it all here in a nice boring format so that people can copy and paste it should they wish, is you need to ingest your synthetic catalog into your Butler. So I made a mildly dubious collection of fakes between redshifts 4 and 8. It's a very old model. Please don't judge me. And then this is how you would upload them. I'm not going to go through it, but the slides are available. So if you want to do this for yourselves, this is an example Python script. Don't put them into my repo. Change the name. Put them into your own. So there are example pipelines, as Lee mentioned. This is what they look like. And this is what you then use to inject your sources into the coad. You would just, here, this is how you run it from the command line. So this is all in pipe tasks format. The first thing you are going to do is you need to specify the inputs after the -i. So here we have two inputs, which is the regular reprocessing run of RC2, because we're going to do a full track's worth of data, followed by the collection that I just put my synthetic catalog into. So you can give it as many inputs as you like, but the more you do, the more confusing it is for everyone involved. So I would suggest just having one which has your input data that you want to add to, and then your one for your synthetic sources. On the next line, you have a -p, which includes the pipeline file that you want to run. After the hash, you can put just the step you want to run. So in this case, we just want to run the coad injection. So we're just going to give it just the one step to do. And then the data IDs you want to process. So I wanted to process all the bands for an entire tract and all the patches. In hindsight, this was a bad call because I didn't start far enough in advance, so I haven't slept for multiple days while trying to get this through the processing. But if you are better planned, that's a good idea. And then the last thing you have is the output as to where you want it to go. So here's a very boring picture that's significantly less pretty than Lee's, but as you can see, we have two fake quasars. They are both under the red crosses, which means that they went into the deep coad calexp where we thought they were. So this has had a couple of subsequent processing steps done on it, and to produce the calibrated deep coad rather than just the initial coad, which is what the fakes are put into by default. You can change that. So if you want to put fakes into any of the data products that we have that it would make sense or wouldn't make sense to put them into, you can. So subsequent to this, we need to run all of the rest of the steps of the pipeline to get to the final data output that we want, which is the object table tract, which is the concatenated catalog from all of the patches in the tract with the calibrated, good, useful measurements available in easy-to-use format rather than AFW tables. So this is an example pipeline. Lee was talking about earlier how you needed to have the you needed to change the connection names so that at each step of the processing, it knew to use the source injection versions. So what you can do is you can take the normal processing pipeline, which has all of the different config options and stuff in it, and then you can add your connections to it, and this should force everything to be in sync and make sure that you are using the same calibrations, the same config options, the same everything, to make sure that you are processing stuff in the same way so that your output comparisons can be useful rather than full of bugs. We will make available example pipelines for people to use, which should be sufficient for most uses, at least to get people started. So this is how we would do the next ones. I ran one step at a time because I wanted to check the outputs of each step as I went along, and because it was one of the first times we've rerun it and I didn't know if it was going to work, but it did. So subsequently to that, we can do some science. The first thing to check is, did the fakes make it all the way through all of the processing steps? And they did. You can see that some of these red circles do indeed have black dots inside them, which is very exciting. The red circles show the input quasars. The black dots is everything in the catalog. Not the entire tract made it through the processing. There were some memory errors, and I just left those patches by the wayside. So we didn't actually get all of them out, but we got a significant portion of them back out again. There is a bunch of science to be done with this. This is a present from my student. I don't want to steal his fun, as interesting as it might be, so I've only done some very rudimentary plots. But you can see that the magnitudes, there is significant magnitude differences here. We expect this because some of these objects are not actually present in the Z-band because some of them are at redshift 8. But the majority of the sources are around 0, which is nice. Why there's such a large spread, I am going to leave to my student to find out, because that's what they're for. So I'm going to give him these catalogs, and hopefully we will have some results before long as to what is going on, how many quasars we can actually find, and give us some idea of how to compare selection methods and what ones will work the best for LSST, whether it comes on Sky. Okay. So I will take I'm going to go do this slide and then take questions, because then I'm going to pass over to Josh. So currently we are reprocessing one tract with each of our regular reprocessing runs. It has the same input every time because we don't care about the input. We want to see how our pipeline changes affect the inputs. So we want to keep that consistent. But that data potentially will be available to people who have access to the RCT runs. You can ingest your own bespoke catalogs and do what you like with them. We are planning to have a few standard catalogs available. They will not be regularly reprocessed, but they will be like pre-ingested for people, so that if you want to just do your first test without having to ingest your own catalogs, we'll have some like random galaxies that you can have a look at. And then the other thing that got broken in the Gen 2 to Gen 3 conversion and is planned to be fixed soon is ingesting your own FITS images. So you can put those wherever you want. So when you have a really beautiful but very complicated galaxy that is beyond the scope of a pile of Circex, you can make your own. I did it with Hypnotoad, very well-known galaxy. So that is what we are currently planning and should have available soon. Okay, questions for my speed but slightly boring demo?
If you could go back a slide.
Yes.
We don't want to steal all the thunder from your students' future plots, but what would be really interesting here would be the zoom in on the top back to a more linear scale, because this stuff down here is a misidentification, and it would be really helpful for the stuff down here to plot output mag versus input mag, and you can see sometimes it was just too dim and you found the nearest thing with bright enough, but the core would be really interesting.
Yeah, and Josh has some of those plots later.
Hi, Sophie, this is very exciting that this has, to see this going through the whole pipeline for the first time, at least for me, that I see it. One of the things, I work for the Dark Energy Science Collaboration. So one of the things that we might be interested in doing is running this at a very large scale, up to the point which this is possible. I understand that the bottleneck in the processing is coming specifically from the processing side rather than the injection. I think actually I studied this a few weeks ago. So in that case, it becomes one of the questions that I was pondering at some time ago is the differences between injecting things at the visit scale versus coad scale.
You have done an Eli because Josh is going to talk about this next.
Okay, all right.
He's got a whole series of slides for you.
I'll skip that question then. And then the second one I had is concerning, I had a question for Lee before concerning alternatives to actually having a model. For instance, injecting either real images or something based on a real catalog. So modelization of objects, let's say in a very deep field. So this will be an alternative, the way you did it, injecting, uploading, like creating it on your own, and then uploading it instead of going through the way that Lee showed, which there was a sort of modeling through the Search. Okay, so that is in place. If I wanted, instead of using a Search model, I wanted to say, include a bunch of models based on a deep field catalog, this will be the way to go. So pre-create it, right.
So it will expect Search. So if you can turn things into Search to put them in, we are not as good as specific science users at recreating their favorite types of model. Mm-hmm. There is no way I'm ever going to make a pretty galaxy, like, or moving objects or smeared trails. Mm-hmm. So we want to provide the abilities for people to make their own catalogs and upload them if you can characterize it by Search, or to make their own FITS images. Right. And upload the FITS images.
Okay, yeah, I was going to ask that. So
because
little snapshots of
little cut out postage stamps.
Okay, great. Thanks.
Yeah, it's beyond the scope of my skill to do justice to people's science. Well enough for that.
Okay, thanks.
I can't talk for Josh and Lee. Maybe you can make perfect objects.
Why FITS images? Do you need a 2D array and a WCS? Is that?
Yes. FITS just seems like the easiest format.
So you mentioned the trailed sources, and I'm wondering, what would you recommend if I want to produce simulated NEO images, for example? Should I create FITS images, or should I just create a catalog with a string of very faint point sources very close together that creates a trail with the required parameters?
Okay. Well, if you want to create FITS images, do it. There is some moving object code in the stack that Zach Langford put in. I am not as familiar with it, so I did not feel comfortable demoing it. Some of that may be able to help you, at least. Ian is giving me a thumbs up, so probably. Another thing that we are probably going to try and get going is to have catalogs that can be done by MJD, essentially, for inputting into visits. So if your object is not moving within the exposure time, it's moving between exposures, then you would just put it in a different place in each visit so that you could see it move across the sky. Anything else? Anything on Slack?
There was one question from Arun about variable input catalogs, but I think that's perhaps best saved till the discussion.
I think I answered as well.
Yeah, maybe.
Okay.
Yeah.
In which case, I'm going to hand over to Josh.
Thank you, Sophie. So I was going to show some work that I've been doing as part of the desk collaboration, actually validating the entire kind of approach of synthetic source injection. One example of which is, can we inject into coads? So we'll see that in a second. So the way synthetic source injection works is we have to use properties that we infer from the image in order to create the new objects. Specifically, we use the inferred PSF to do a convolution. We use an inferred WCS to place the objects at the catalog IA deck. And we use inferred calibration products to get the right magnitudes. And of course, these are all things that we inferred from the image, but that's not exactly the same as the truth. So one test that I've been working on is, well, what if we had the truth? In DP0, it's a simulation. We actually do know these exactly. So the study here is comparing what happens when I run the SSI pipeline versus just rerun the simulation that produced DP0, but with the same objects added to the catalog. Right, and then we can see what's different. So I've done this for actually just one DC2, or sorry, DC2 is the desk name for DP0, roughly. One CCD image on a hexagonal grid that was larger, and yeah, the caveat here is that I did this with the kind of the original source injection framework, not the new things that Sophie and Lee were showing you earlier. But I think that the underlying architecture is still Gaussian. I think a lot of the results still apply. So here's a quick demo of some of the images that come out of this. So on the left is an original image from DC2. In the middle is an image where I ran the source injection pipeline, and then on the right is where I just augmented the input catalog to the simulation. And if you look very carefully, I'll give you a second, you might be able to find a new object on the right side there. And then if I show you the difference image, you can see if you were right, see how many you actually found. And there it is. So from that point, I started looking at some of the measurements that came out. So here's an astrometry comparison. So this is looking at the augmented catalog image. What is the astrometric difference between what was measured by the pipeline and what was the input in the catalog? And you can see that our astrometry is sensitive to noise, for example. These aren't zero, but the critical part is actually what happens if you compare that to running the source injection pipeline. That's what's actually of interest in the test here. And if you look at these by eye, they look pretty similar. So we're doing a pretty good job. And sorry, I haven't quantified that exactly for you, but that's good news for the source injection, I think. Here's another example. This is for photometry. So this is one of our many, maybe not the best possible ways of measuring photometry, but using a Cron magnitude for galaxies. But again, the critical part is it the same when you use the new simulation versus running the source injection pipeline? And yes, there is some scatter, but you get more or less the same set of points. So it looks like things are stable in that measurement to. And then, finally, I also looked at measuring object, our detection completeness for both techniques. You can see the comparison here. They are a little different. So the injected, using the source injection pipeline, it looks like it's a little bit deeper in this case than rerunning the simulation. But I think one thing I discovered through this process, which was a question brought up earlier actually, is I'm pretty sure I did not have the same configuration settings when running SSI as when running the original pipeline. And I blame that for some of these differences here. And then, just going through the bullet points here, some of the other things I learned going through this exercise. The injections, when we're adding them to the images with Gaussian, they're perfectly smooth right now, so there's no added noise, Poisson statistics noise in the injections themselves. So that's a difference that we should track. As was mentioned, we're not currently modifying anything in the variance plane, so that's a big to-do item, I think. And then, of course, what I was actually trying to test here is a source of difference is using the inferred PSF, WCS, and calibration instead of the true one. So that's the first study. Maybe if there are any questions on that first, it's Eli.
About the variance plane, and I wonder if that's what's going on with the detectability.
Maybe.
But if you go, have you looked at the errors on the flux estimates?
Yeah, those definitely.
Are they
there
way
are
off?
differences.
What?
Sorry, I don't have the plot. Sorry, but yeah, that you're right.
And that's where the variance plane comes in.
It definitely shows up in the error estimates. Yeah, that's right.
Okay. Eventually, but I know that the way that we estimate the errors uses the variance plane and expects those to be modified with the source counts.
Yeah.
You should just be able to add in quadrature, source counts to the variance plane.
I think it's a little tricky depending on whether you're adding it to the coad, for example, or the CalX. There are details, but yeah, we should.
I don't know about the coads.
Yeah. we should figure this out. Yeah. All right. The second thing I wanted to talk about was this question of does co-addition and source injection, do they commute? Can you inject directly into the coad, or should you inject into the single exposures and then coad those? It'd be nice if we can inject straight into the coads, because then we can skip part of the processing, creating all the, recreating coads of all the injected objects. So that's the question. For this, I also included a link here because I have been doing this study using the batch processing service, the BPS framework in the stack. So this is, at the moment I've only done one patch, but this is now at a state where it could be scaled up using BPS quite a bit. Okay, so here's the example. So here's a color image from DC2 on the left. In the middle is a image where I injected into the individual visits into the CalX and then co-added them. And then on the right is an injection straight into the coad. And let's see, what did I do here? I think this is now, if you subtract the original image, so you're just looking at the injected objects in both cases, it looks similar. But if you now take the difference between right images, that's what you get on the right, this very colorful difference. So you can see some things going on here. when we do an injection, we pick out a square region, basically, in which we modify pixels. So if you do that in the coad, you get a region that's aligned with the coad pixels. If you do it in the individual visits, you get all kinds of rotation angles from, however the orientation of the individual visits were. You can also see edges in the individual visits where, we might have added an object that was right at the edge of a CCD, and so it didn't cover the rest of that footprint in the coad. So this looks maybe a little scary, but I don't have any scale bars on here for you to actually know. But it's hard to do that in color. So here's just one band. I think this is our band, maybe. So again, the injected image on the left with a scale bar that goes 0 to 1. The injections only in the middle with a much compressed scale bar from 0 to 0.1. And then this commutator object that I was actually interested in studying with a scale bar that's 1,000 times smaller than the original image. So I think that's okay. We're probably okay. These differences are coming in at the level that's, parts per thousand of the kind of the original image. Yeah, Eli, please.
Back again. Is this something that cell-based coads would also help?
Yeah,
especially
I think
with the edge injection.
Because you would avoid this edge question. So Eli's question was, if we use edge-free cells, which some of you may have heard of, would this comparison be cleaner? And I think the answer is yes. You would get rid of some of these artifacts by not having edges of CCDs run through the objects that you're trying to simulate. Yeah, Ian.
Another implementation question, is Ian Sullivan talking. With the injection into coads, do you inject just once, or do you inject once for each contributing Alex?
So the code is the same. So it uses the coad PSF to do the convolution, and it assumes, that the sin here is that it assumes the coad PSF is constant and valid over the extent of the object that you're injecting, which is not actually true. Yeah, Michael.
And in theory, this is telling you exactly what's wrong with your coad PSF model, right?
It's certainly related to that, yeah.
But I mean, in the sense of the edges and what's not consistent, and your statement that, you ask the coad for a PSF is like, here you go.
Yeah.
Don't ask questions. Here you go.
Exactly.
And anyway, but I think my real question was, this is interesting, but like an answerable question. Yesterday, day before, Nate was telling us about how to write metrics and all that stuff. What's the thing here, and really the point more broadly in the community was, there are a bunch of types of metrics that come up with doing these source injections. Go ahead, Sophie, you know where I'm going.
Okay, I don't know if people online could hear that. Sophie says, wait for the end of the talk, Michael. Yeah.
And one following up on that, the edge-free cells will also make a much simpler coad PSF, so there won't be.
Right, it should be much more
It's just
valid.
not just edges, but like simpler and constant.
Yeah. Okay. Right. So yeah, I think we've talked about these. Y is the commutator, not 0. We inject into square boxes that are round, rotated some of the time. There are edges. Yeah, let's go on. So that was the image. I also ran this through measurement. So here's looking at, a comparison. What is this one? This is just photometry. Measurement minus true for UGR IZY. In this case, directly injecting into coads, and then here directly injecting into the calyx. I can blink back and forth. What happens is for most of the objects, many of the objects, it's really rock solid. There's zero difference that you can pick up. And then there's a tail of things where it matters. So here's the plotting those directly against each other, the I-band C model magnitudes. And then I just included one more plot, which was the completeness. I don't know if you can even tell on the projector there that there are two lines, maybe if you look right here, that the completeness in both ways of doing the injection is very, very similar. All right, and then so my conclusions, which I think we've talked about these before. We should add the Poisson noise. We should modify the variance plane. We have to be careful with making sure we're running the same configuration on the original and the source injected images. That should get easier with the new modular framework that Sophie already mentioned. And then, there are some subtle differences in, injections into coads or coads of injected images. There are some small differences, but it's mostly pretty rock solid. And I think that's my last slide. Yep. Any other questions?
Make a really quick comment. So, I mean, it absolutely makes sense to add the Poisson noise and then modify the variance plane, but it's so good that you didn't do that yet, right? These null tests that you're showing us make sense to do in a noiseless regime, and then you can see if there's something you're worried about in the patterns. But the natural metric for your commutator, once you've decided if there's a bug, is basically in the units of the noise, and then we're going to see much less pattern and realize we probably don't care anymore.
That's true. Yeah. Thank you. Okay. Take over, Sophie.
So I'm going to sneak in one extra slide and then trigger the discussion. I think I have to go out and then back. Here we go. So some of you will have been to Nate's talk or been around us recently, because Nate and I have spent a lot of time developing analysis tools, which has metrics and plots in it. And I have obsessively made a very large amount of plots. And you are right, fakes is perfect for that. And soon we will have, soon is a relative timescale, we will have fakes, plots in analysis tools where we will be making automatically plots and metrics from the regularly reprocessed runs with synthetic sources. This is an old example plot. You can see here input magnitude versus the magnitude difference. You will note that the scale is in millimags and that the median in millimags is less than 2. So we can actually, for stars, for just stars, no galaxies because they make our numbers look bad. Yes, exactly. Who wants them? We can recapture output and input, like the magnitudes, pretty well. This is PSF magnitudes for stellar things. And we will hope to have plots like this easily available, and in a pipeline where if you add your own fakes, you can just say at the end of adding these fakes, please also make me plots for them, so that they will automatically generate you a base set of metrics and plots for verification of your data. That's the dream. Yes, Lauren?
Sorry if I missed this, but when you're doing plots like this, when you inject these sources, are you injecting them in a non-detected region of the image, or is it all random?
Just wedge them in at random locations.
Isolated stars necessarily?
Not necessarily isolated stars. So that's probably some of those outliers. Okay. They're just shoved.
Great. So in terms of the language of all that, like the selectors here, and are you doing output versus input? How do you do the matches? All those seem like things that that's really where my brain starts to hurt. And if you have like all those options, we can have much cleaner discussions, like the classic, like recovered versus that. Well, if it's a mismatch, you get a thing that's totally the wrong thing. Different matching algorithms, all that stuff would be fantastic.
Yes. This is just a straight ARIAN deck match with nothing fancy in it, because if it's going wrong, if it's 2 magnitudes out, I kind of want to know. So I didn't want to put like some photometric requirement in the matching, because particularly when you're testing new code, like it could be 2 magnitudes out because you made an error. So yeah, this is just closest source within half an arcsecond radius or something. I have astrometry residuals and things like that if we cared about them. But yes, all of that does need thinking about. Okay. So if there's no more questions for anyone, I would like to hear from people what you think would be useful. I have like an example question here to start off a discussion, but I'm happy to hear about anything on the synthetic source topics. What else would we need to include that would help you do your science easily, or answer your data questions easily?
So Lee asked me this morning if I could say a few words about our experiences. So just a little bit of background for everybody in the room. We were trying to inject very large sources into the images prior to sky subtraction to sort of track how the sky subtraction was working. And definitely what we found the most useful was the ability to just upload whatever we wanted, because we were trying to inject very crazy things, including stamps from cosmological simulations and also half-degree size stamps of ICL models and stuff like that. So absolutely, it sounded like you guys haven't implemented that yet in the current version, but if you're going to, that would be very helpful for us. The other aspect is, since we were doing large extended sources, we were mostly interested in surface photometry for our metrics. And the issue that we've run into at this point is I ended up having to do my own surface photometry because of contamination from other sources in the frame. Using the aperture photometry that comes out of the catalog, there's a lot of noise in it. So I don't know what the solution to that would be, or if anybody else would be concerned enough about something like that for you to come up with a solution. But I just thought I'd kind of bring that up as one of the potential issues that we're having trying to devise metrics using these kind of large extended sources.
Yeah, I'll say a few words on that. So on the first point, Aaron, so definitely, yeah, image injection is definitely on our priority list. I think it's our kind of catch-all. You know, if I want to do this really complex thing, can I do it? And the answer we're going to give is yes, as long as you make your own images. So that's the kind of definite yes for that. And there's no kind of strong technical reason why that doesn't exist just yet. It's just a matter of time. We haven't got around to testing that fully, so we weren't confident putting that out today. But with regards to your second point and metrics and surface photometry, yeah, we have to. There was a question earlier as well about efficiency and how long it takes, or maybe on Slack, how long certain things take to run, and doing a good job of the kind of surface brightness profile analysis that I know that you're interested in is, as you know, computationally expensive, can be computationally expensive, and we need to kind of think of a way, if we're able to produce something with the catalog outputs we have that you know satisfies your needs, that would be great. But I don't think we have any plans to write you know kind of in-depth pixel level surface photometry code at present, because I think it would just be too computationally expensive to run. But if there are others in the room that have kind of a better idea of how best to do that, you know, we'd love to hear about that.
Thanks.
Have any more questions, comments?
Yeah, so I can. There's been some discussion on Slack, and I'm not sure if it's worth. If there are no burning questions, if we can go back and look at those for a second. So, Arun was asking about the input catalogs, and in particular, time-dependent models. I'm not sure if Arun's in the room or where you are. You want to say more about that, Arun?
Yeah, I'm online here. So because you are registering this input catalog for a given tract, I was wondering how I should be registering a catalog if the magnitudes would change depending on which visit I want to inject into. Like say if I want to inject a supernova or any other time-dependent source. And a related question was, even if the source is static, but I want to inject it into all 6 bands because I want to test color on it, then I would still want to register a different catalog for a different band. Is that still possible?
So,
Yeah,
sorry.
No,
I'll answer a little bit. Oh, great. So at the moment, you put in a different magnitude per band into one catalog. So if you just want different magnitudes in each filter, you just tell it that the G mag, the R mag, the I mag are all different. And that is currently there. For the putting things into different things into different visits, we have a vague plan of making catalogs that can be registered per visit so that you can pre-calculate how your object is going to change per visit. Or you can just call them 2 different things if you have a very simple thing, like say you have one fake catalog, one source injection catalog with supernova and one without, but it's just like 2 or 3. You can just give them different names and add them in at different times. Put them into different collections for comparison is the current workaround. Sorry, Lee.
No, thank you for that. I mean, that's great. The one thing I would add to that is, so there are a couple of config options. We haven't discussed them today, but they're present and they can be used right now that allow you to sub-select sources within an input catalog to only use those for a given run. So one of them is the select column, and one of them is the visit column. So you can add to your input catalog another column called visit, for example, where you give the visit ID. And then you can switch that on, and then when you run through, you can say, okay, only use, only match to certain visits, or only select this select column if you want to do it that way. We haven't tested that very much. That is functionality that was there in Gen 2, and we've mapped it over. I don't think that goes all of the way towards doing what you need to do, but I think something like that is the beginning of the way to go. But yeah. Something we should definitely look at testing. If you have a good kind of solid use case or something we can work on, that would be good to look at.
I was thinking about, there's this generalized, sorry, was there someone else online?
No, go ahead.
The generalization of, I have an SED as a function of time and some ephemeris, right? Okay, that's a little, but we can sort of go through that. But I was just thinking for the synthetic source injection and the SED might be a really nice way to start testing out when you get to the point that you're reporting transmission functions for individual images and testing that part. So this is not a thing to do next month, but like as Eli's in the room, right? Right, but this idea of getting to, once you report the, I forget what Greek letter, but the SED transmission function for an image, that getting that framework up, being able to test by actually injecting them that way would be nice to sort of just connect that whole thing. So for the immediate short term though, right now I just say, here's a magnitude. Someone calibrated this with some just broadband AB, or actually it doesn't even have to be AB, it was just whatever the catalog says. Is there a small step to being able to easily say, here's the transmission function I want to use, or here's the nominal transmission function and I want to modify it in this way?
Apparently, that's up to the user. We don't have that built in for sure. Another thing you can start thinking about with SED dependence is chromatic PSFs, and we don't have that either. So if you wanted to simulate or inject something that has DCR in it, I don't think we have a good way to do that right now.
Yeah, that's what I was going to say. Is the DCR and something is more complex, and so if you're talking about the injector will know the color per band, and you can then you yourself do the integration and predict what magnitude it should be for the transmission function, and say for this visit it should be this magnitude, and that seems like it's supported right now. What is more of a challenge is if you're worrying about the color of the object within the band and those effects. And I don't know. I think that IMSIM is probably the way to go for that, the resimulation thing. But I don't know. Yeah. But for right now, you can do the integrals yourself. And
I think that comes under when you get above a certain level of complexity, make your own FITS images. For now, at least. Okay. Any other comments from anyone online or in the room? I truly would love to believe that our code is completely featureful and perfect in every way, and that we've made you all very happy, but I don't, sadly.
I guess another active topic of conversation was about the variance plane, but I think we've discussed that quite a lot, and how best to do that, and whether it's computationally feasible, too slow, how to handle that properly. But I think there's been a lot of chat on Slack about that.
Another thing I would suggest maybe as a stretch goal that might be cool is going back to Arun's question, would be just if you could inject, given a parameterized model for some variability, just calculate the appropriate meg on the fly for each visit then. I'm not sure how complicated that would be or how much parameter space you would need to enable different types of things, but that could be really useful too.
It's me again. So I don't know how much this affects anybody else's science, but I thought I'd mention it because I just remembered it. When I was doing the surface photometry of the models we injected two kinds, ones that were face on and then others that were inclined roughly 45 degrees. And I found that on the inclined galaxies, the central surface brightnesses of the injected models were always off from what I thought they should be given their Sirsic parameters. I tracked that down to, I think it was GalSim. There's two ways you can do the inclination. You can either just give it an axial ratio, or you can give it an actual inclination parameter, which then adjusts the flux. And that was what was going wrong, is I think the inclination that was being used in the injection software didn't take into account surface brightness changes based on inclination. So I ended up just making my own stamps, doing it the other way so that all the parameters would come out correctly. Again, this is a very specific thing. It might not affect anybody else's, but if that's still a slight bug, then that would be something to look into as well.
Yeah, that's a great point, actually. So GalSim is very powerful, and we're leveraging kind of a small corner of it right now, but getting this kind of feedback is really useful. I think should be quite trivial for us to enable that kind of support. So you could specify either or, and if that's something that's in high demand, we could certainly look at adding that onto our to-do list, I think.
Hi, this is Ian again. My question is about a development of additional metrics and plots using synthetic sources. For example, hooking up completeness plots can be automatically generated. That's part of the plan. Wonderful. There was nodding for online people.
That is That is part of the plan. I have example plots. You can see them if you want. But if I included every plot I've ever made in this talk, we'd be here all day and you'd be bored.
So I apologize that this is a bit off topic, and it simply stems from curiosity about algorithms. So could anyone explain briefly the edge-free cell algorithm that was mentioned earlier? Seemed like an interesting concept.
Okay, so I'm going to wave my hands here. Okay, so the traditional coad, what? Okay, yeah, I can talk quickly. Not as fast as Jim Bosch, but the traditional coad patch size is something like 3,000 or 4,000 pixels on a side, and you put all the detectors from all the visits that go in there. And now when you go to LSST, you have all these rotations and you have all these edges. So if you go down and make your patch, which we call a cell, small, 150 by 150 pixels we're talking, then that fits well within any detector. And so you throw out, depends on how small you make the cell. And this is really focused on weak lensing. This is not focused on, big galaxies, but I'll get to that in a moment. But in the small cells, you go and only if the cell that you're choosing fits completely within that detector with no bad amps, no defects, no edges, then you put it in. Rotated all of this. You lose 20% of the data or whatever, but you gain in systematics incredibly because now over that cell, you have basically a constant PSF. And you don't have any edges, and so this makes the weak lensing analysis a lot more robust, a lot faster, and can just run like that. And then there's overlap regions. So the cells are bigger than the unique regions, and you tile these up, and then you can actually then make a patch out of these cells, and then you also have a simple PSF. It's a little checkerboard of simple PSFs, but that's better than what we have now, which is actually, if you've ever looked at this HSC Ultra Deep especially, which has tons of visits in it, then every photometry has this flag inexact PSF because you just don't know. And so how this will work for bigger objects that transition across cells, larger than basically, the buffer width, which is TBD. We haven't, so we're probably going to be making both sets of coads, the traditional ones and these edge-free cells. But for anything that can use those edge-free cells, recommended, because it'll be, again, then you can just do your analysis on the coad, one PSF, simple projection, and you're off to the races.
I think that is us, pretty much. There's no final comments anywhere. I'll say that I'm leaving tomorrow, but I'm around the rest of the day. Lee is in the ether somewhere. But we are all reachable on Slack, and on the normal LSST Slack, you don't need to stay on the meeting Slack. And we have a Slack channel. There's a couple of synthetic source injection Slack channels. I would prefer if we kept discussion into the general one and slightly less in the desk one, just so that everybody can see it. We'll stick a link to can we do that? Can we link between colored Slacks? I don't know. Anyway, we'll put the name of the Slack channel into this Slack channel so that you can find us in the normal LSST Slack if you want to be kept updated, share your plots, complain about bugs, any of the things. We'll put that there. Okay. Thank you, Lee. Thank you, Josh. And if that's done, I will give you 4 minutes of your lives back.
All for great discussion.
So you have this.
That was fun. That was good.
I was just saying that I was impressed but unsurprised that you had already managed to get the links into the Slack channel.
Yes. Oh.
Right, I don't know whether to leave your face here, so if people have questions for you, they can ask you while they're filing out or not.
I think Slack is fine, but that was really useful. So yeah, thanks for Sophie and Josh. Good fun. Enjoy the rest of your day and week.
Bye, Lee.